Hello, everyone. Welcome to the virtual talk on a symphony of data-based, physics-based, and agent-based models to create a COVID-19 safe corridor for international travel, authored by myself, Prathamesh S. Desai, and co-authored by Nihar Sawant and Achal Khilnani. Here is a brief outline of my talk. I'll start by introducing the problem and would lay an objective which we would like to achieve through this talk. Then we will spend some time in understanding what I mean by a COVID-19 safe corridor. Then I'll delve into three models to answer three questions, which would in turn help us to develop this COVID-19 safe corridor. And then I'll summarize my findings. COVID-19 or coronavirus disease was declared a pandemic by World Health Organization in early March of 2020. Now, due to the fact that world is a much more connected place today, more than ever, this pandemic grew fast and far, and it has already claimed around 3.89 million deaths worldwide. During this pandemic, the reliance of people on public transit systems for city and state level transport went down considerably. However, for the foreseeable future, the reliance on commercial aircrafts would continue for international travel. Thus, there is a need to create a COVID-19 safe corridor as far as international travel is concerned. The objective is to develop computational models that would help us to design such a COVID-19 safe corridor as it relates to international travel. Now, what do I mean by a COVID-19 safe corridor and how to achieve one? The way to develop this corridor is by employing computational models which run on either regular computers or supercomputers, and they help us to address three specific questions. Now, these models can come in different flavors. These can be data-based models, physics-based models, or agent-based models. The very first question which we would like to answer is, should a person be even taking the trip to the airport for the international travel, considering the COVID-19 situation in his or her locality or city? If he or she decides to take that trip, once at the airport, which seat should he be occupying in the flight so that he's safe from COVID-19 on the flight? And then finally, once he reaches his destination, his or her destination, what should be his or her last mile connectivity option? And while answering these three questions, what we would end up doing is developing a COVID-19 safe corridor. So there are three models which will help us to answer these questions. The first one is a database model, second is a physics-based model, and lastly, there is an agent-based model. The first one helps us to answer the first question on forecasting COVID-19 spread at a local level. And this is an artificial intelligence model which has been published in the Journal of Expert Systems with Applications. It makes use of Google's TensorFlow library, and IBM Watson is used to extract sentiment of news articles. The entire code module is available on CodeOcean for reproducibility and transfer learning. Why, first of all, is there a need for such a model? This is because of the fact that the existing forecasting models, as far as COVID-19 is concerned, have certain issues. These models work at large geographical and temporal scales, but they are not as reliable at local, county level, and at a daily scale. These models make use of number of positive cases instead of a normalized value, that is COVID-19 test positivity. Positivity is a better reflection on what really is happening in a certain area with respect to COVID, as we cannot control the number of people who would be willing to take COVID-19 tests. None of these models take into account human sentiment. And by taking into account human sentiment, we get some spatial dependence of COVID-19 spread in a particular region. There are some models which take into account social media posts. However, as we know, these posts will have lots of noise. Thus, I ended up developing an artificial intelligence which made use of news sentiment at a local level and COVID-19 positivity data to predict COVID-19 positivity into the future. Now, this is a screenshot of IBM's Watson news discovery tool, which helps us to query news articles and look at their sentiment. The query used was, is the spread of coronavirus under control? and look at articles which have Houston in their URL, because I'm in Houston presently, and then give me the sentiment, average sentiment of that article, or the total number of articles. On the right, you will then see a typical or a sample score on this particular date was negative 50%. And the articles which were returned, around 102, some of them are clear. Even by looking at the headings, it's clear that these are negative sentiment articles. Once you have that, now you can marry it with COVID-19 positivity to predict into the future. And the way to do that is through neural networks. Before that, I would like to talk about different types of convolutions. Regular convolutions are ones in which if this is an input layer with time increasing from top to bottom, subsequent hidden layers look at information not only at previous time steps but also at next time steps. This is not suited for temporal data, because this would mean that we are looking into the future to get something into the past, to predict something into the past. So to avoid that, there is something called causal convolutions, which look at data only into the past to predict into the future. And a specific category of causal convolutions is dilated causal convolutions, where you skip intermediate data and the subsequent layers are then able to look at a much longer time series than in the case of causal convolutions. So in this particular study, I made use of a multivariate CNN with dilated causal convolutions, and this AI is named as SITLA, and it stands for Sentiment Informed Time Series Analyzing AI. A window size of 16 days was used because of the incubation period of virus being 16 days. The architecture is shown as shown here. There's an input layer, a few hidden layers comprised of dilated causal convolutions, flattened layer, dense layer, and then a final single output at a single day in future. Now, these are the predictions of SITLA for the county of Harris. That's where Houston is located. Now, it's a pretty informative chart, and I'll walk through this in a slow fashion. On the left axis is COVID-19 test positivity and news sentiment expressed as percentage. And on the right is the number of news articles returned by this ABM Watson news discovery tool. Is just multiplied by the sign of the sentiment. Connected red dots are the ground truth for COVID-19 positivity in Harris County. Square data is for the news sentiment, and bar chart is for the number of news articles. Initial 75% of the data was used for training. Out of that, 10% was reserved for validation. The rest of the data was used for testing, and a forecast for around 16 days was generated. A continuous black line is the predictions from SITLA. As you can see, it's fairly well in training data set with a mean absolute error of 2.76. In the test data set, mean absolute error is a little more of 9.6. And for the forecast, what I did was, what happens if you have a sustained negative news sentiment and a sustained positive news sentiment in these 2 weeks? Then what you get is a cone of uncertainty, where if you have positive news sentiment, people get out and then the positivity goes up. If you have a sustained negative news sentiment, it helps you to control COVID-19 positivity. And these red dots are again ground truths, which were laid on top after the forecast was made. You can see SITLA is able to capture this trend in a much reliable fashion, as opposed to a published third model which underpredicted COVID-19 positivity by a lot. So this proves the fact that it's better to look at local level and on a daily scale, rather than looking at a state or country level, and the time scale is of the order of weeks or months. That's the first question. This model will help us answer the first question of, is it even feasible for you to travel to the airport, considering the COVID-19 situation in your region? Now, let's move on to the second model. It's a physics-based model, and it helps us to answer the second question of which seat to occupy on an air flight. This study has been published in Building Simulation Journal and makes use of ANSYS Fluent and the simulations were run on Pittsburgh's supercomputer. The problem physics which this model solves is the flow physics using incompressible Navier-Stokes equations, where you have the continuity equation and momentum conservation equation, and temperature distribution in the cabin using energy conservation equation. And the transport of orally or nasally released pollutant, coronavirus or carbon dioxide, is calculated or is solved using the mass transport equation, which looks like this. The boundary conditions for the two cabins which we looked at, the left one is an A380, that is an Airbus 380 cabin, and the right one is the Boeing 747. These are the two largest intercontinental aircrafts, and we looked at all three cabins: first class, business class, and economy class. The boundary conditions are as shown in this image and described in this table. Now, human bodies were replaced with rectangles which were a source of heat, and the pollutants were released from the nose level of these bodies. Only one half of the section was solved using a symmetry boundary condition. So the model itself is a RANS model with pollutant transport. So over on the left, we are looking at an Airbus A380's economy class cabin, where we are going to solve flow field only in the left half of the cabin. And with the inlets being here and outlet being here, you can see there are two eddies which are getting from, one is on the left side and another one is on the right side. If we look at the Boeing 747's economy cabin, we see a large central eddy getting formed in the middle of the cabin, middle of the half part of the cabin. Then if we look at the pollutant released and how does that pollutant diffuse spatially, on the left is the data for Airbus A380, and these points are where the noses of these passengers are located, and on the right is the data for Boeing 747, is the simulation output for Boeing 747. When we combine these temperature fields, flow fields, and pollutant fields and develop a ranking scheme, making use of ASHRAE standards, and the ranking for Airbus A380 economy cabin looked like this, where the seat in the window got the first rank, and surprisingly the middle seat got the second rank, and the worst one was the one in the center of the cabin. For Boeing 747, surprisingly the middle seat on the left side of the seats was the first ranked seat, best suited seat, and aisle seat was the second ranked seat. Now this brings us to a good point where we can stop and examine that the fact what commercial airlines are saying is to leave middle seat vacant might not always be good. It is highly dependent on the flow field which is developed inside the cabin. In certain cases, it might be even good to occupy the middle seat and keep the aisle seat vacant, as in the case of Airbus, or leave the window seat vacant, as in the case of Boeing 747. So now this model is something which would help you to answer the question of, if you are going to take an international flight, which seat is best suited for you. And this brings me to the final model, which is an agent-based model. This will help us to answer the final question on last mile connectivity. The study here is under preparation. It's on agent-based and Bayesian modeling of PRT system for a post-COVID-19 India. It's authored by me and Achal Khilnani. And we are using Ultra City Mobile software to model a personal rapid transit system, and NorSys software will be used for Bayesian modeling. Now, why is last mile connectivity even a concern? If someone takes all these measures to safeguard himself or herself from COVID-19, and after reaching the destination, if the country is a developing country like India, last mile connectivity looks something like this, where it is a highly overcrowded public transit system, and it's obvious that you will catch COVID-19 in these kind of public transit systems. So a better last mile connectivity is needed, and personal rapid transit, or PRT, offers such a solution. where these pods, think of it as pods on tracks, highly personalized, but still in a public transit scenario. These pods can be cleaned in between trips without affecting the entire system. Now, this is not true for rails, monorails, trains, or even buses for that matter. Once a bus or train is taken out for cleaning purposes, it affects the entire schedule. These pods look something like this, almost like bugs, but they're pretty neat, and the size is enough to carry 4 to 6 passengers for a single family. And the stations are offline, like they do not interfere with the continuous travel of these pods on the main loops. So this study involves developing an agent-based model of personal rapid transit system for an international airport in India. Now, ABM, or agent-based model, is based on principles of cellular automata. A personal rapid transit includes on-demand routing of agents, that is these PRT pods, to minimize passenger wait times. Also, offline stations help to minimize travel times. And this technique allows us to explicitly model special effects such as sanitation time for each pod in between trips. Once put in place, the model looks something like this. On the top right, I'm showing a proposed PRT loop for the proposed Navi Mumbai International Airport. The loop is shown in black. That's the primary loop, and the loops in gray are feeder loops, and the stations are shown by these dots. And on the bottom right is a sample simulation for PRT traffic. As you can see, there is a pod coming, waiting for passengers to get in, and then it leaves. And then there were other pods which continued to move without any interference from the station. This is still an ongoing work. So to summarize, it is possible to create COVID-19 safe corridor using computational models and supercomputers. And it is possible if you are able to answer these 3 questions. As, should I make a trip to the airport? Yes or no. That answer comes from data-based artificial intelligence model. Which seat to occupy on the flight? This answer comes from a physics-based model. And finally, what should be my last mile connectivity? If it is a personal rapid transit system, the designing of that system can be done using an agent-based model. Here are the references. The first 2 are published in journals. The third one is under preparation. Then we would like to acknowledge efforts or assistance of Andrew Keynes, Shahbaz Sheikh, Abhishek Sinha, and Dr. Sadbir Singh. Thank you. That's my talk. And if you all have any particular questions, you can ask us on email, and the emails for 3 of us are listed here. Thank you.